All right, the topic here is a study I did on landing very large payloads on Mars. It's kind of a practical how-to hand calculation thing. It's not polished. This is warts and all. I put some qualifications up here uh, just to let you know I really am qualified to have done this. Uh, I had a 20-year career in aerospace defense weapons work, followed by a 20-year career in mostly teaching with a little CE and some aviation work. I'm now retired, but I kept up those aerospace abilities all these years, and that's what I employed to do this study. Now, here's the problem. There is no infrastructure at Mars yet, other than some observer satellites in orbit and a few rovers or landers on the ground. There, infrastructure is needed for any sort of self-sustaining anything that we might put there on that planet. And initially, all of that has to be sent from Earth one way. The question is, how do we land big one-way payloads on Mars? That's because it has such a thin atmosphere. This was not previously done with the probes. About the maximum that we've ever landed there is those 1-ton nuclear-powered rovers. Uh, you got to think outside the box, and the box has been coming out of the entry hypersonics direct off the interplanetary trajectory at a high altitude in the thin Martian atmosphere, somewhere above 25 kilometers, so that you have time to actually deploy a chute and expect it to actually decelerate you. The bigger your payload, the bigger your ballistic coefficient, and the deeper down in that thin atmosphere you come out of hypersonics. And once you're much above a ton, you're going to come out too close to the ground to use any kind of a parachute. You won't even be able to get it out, much less have it slow you down. Got to think outside the box. Now, the way I did this is I used a minimum energy transfer orbit. This is presumed to be unmanned cargo sent to Mars, so you don't have to get there faster. That reduces the size of the launch rocket. I assumed average planetary conditions, min-energy home and transfer, and I'm just dropping off the payload to be landed. It's all one way, one time, one shot only. The end of entry conditions, if you're big, you're going to be low altitude and you're not going to be able to use chutes. You're going to have to do some kind of rocket burn to land. That's what this study was all about. All right. Now, when we're talking about minimum energy transfer, we're talking about departing from low Earth orbit. We're going to assemble this thing in low Earth orbit. We're going to do a departure burn that puts us on the interplanetary trajectory for Mars. And then from there, we got to do a couple of course corrections. And we're going to do a direct entry into the Martian atmosphere off the interplanetary trajectory, which is not any different from what we've done before, except that I'm going from Earth orbit and not from the surface. Okay, we're going to assemble this thing. It's this big thing, so we're going to assemble it by docking in Earth orbit. All right. There's no arrival delta V that the rocket has to do. It's just a direct entry, but you do have to land. All right. The speed at entry is going to be a little over 5 kilometers a second, so you're entering the atmosphere above Martian escape speed. Now, as I indicated, the entry, descent, and landing is going to be the tricky part of this. Now, getting entry at a shallow angle, that's fairly well known. The point is where you come out of the hypersonics. You're going to be doing about Mach 3 at somewhere like 5 or maybe 7 kilometers up. Your speed is going to be on Mars. Mach 3 is approximately 0.7 kilometers a second. What I assumed for some just back of the envelope calculations was that we're moving downward on a slant path at about 45 degrees below horizontal at the end of hypersonics. We had trajectory group in hypersonics. All right, now I used some simple high school kinematics, and what I got for the 5 kilometer a second altitude was that we would need to be decelerating about 35 meters per second squared. All right. If you're 7 kilometers up, that reduces to 25. So we're looking at somewhere between 3 and 4 standard Gs. It's a little higher if you're at 5 kilometers. It's a little lower if you're at 7 kilometers to reach zero speed by the time you hit the ground here. All right. Now, what you're looking at with Mars gravity, and this is just adding them instead of vectorially adding them, you just add a fraction of a G to these numbers here, and this is what you're going to feel. Your payload's going to have to be able to resist 4 Gs or thereabouts in order to make this landing and not be damaged. All right. If you're undecelerated, you've got like 10 seconds to impact, maybe 15. That's not enough to deploy a chute and expect it to do any good. That's what I'm talking about. With big ballistic coefficients, you're coming out low. Now, here's the velocity that you have to kill. I got to come up with some kind of a velocity requirement for the landing burn so that I can calculate an amount of propellant. Okay. Now I got to kill 0.7 of a kilometer per second and a little bit of altitude. There's some gravity and drag losses there, but compared to what I'm about to show you, they're minor. That's on Mars because of the low gravity and the very thin air. All right. So as we come down, we need to stop and hover and divert clear of obstacles and hazards on the surface in order to land. As I said, there is no infrastructure there. I don't have a landing pad to land on. I got to make a dirt, rough field landing, and I need some kind of robot capable of recognizing these hazards and diverting the craft to clear them. The same way that Armstrong diverted around the boulder field on the moon when he and Aldrin landed on the moon in Apollo 11. Got to do that with machines instead of people. This is unmanned. All right, so we're going to stop and hover. That's going to cost some over here, and the best way to do that is to apply a factor between 1.5 and 2 to the DV to get your mass ratio effective DV you need to design into the vehicle. Okay, now here is the concept. We've got a lander and a transfer stage. This is the article that we're going to land, just shown as a dummy here, just gray. And then I need a transfer stage to take it from Earth orbit and get it to the entry point, the direct entry point on Mars. All right. So the payload needs a landing DV. All the rest of its braking is aero braking in the hypersonics. All it needs to do is land, and it's one shot. Okay. I need some high energy propellant to depart from Earth orbit. That's over a short time interval, so I'm going to use hydrogen and oxygen for that and deplete them. And then I need an ullage solution to light those motors, and I also need some kind of propellant solution. It doesn't necessarily have to be hydrogen and oxygen. It could be storables to do the 2 course corrections to get me there. All right. Let's see. Now this is just a reminder. We're presuming no infrastructure on Mars. We're making rough field landings in the dirt and the rocks, whatever, wherever we're going down. We're going to start with some good guesses and then iterate to solutions. The rough field landings are going to size the dimensions of the landing craft because of landing stability. I don't want this thing turning over. And I've also got to have some size pads for it to sit on the soft dirt with. Whatever I come up with for the lander is going to size the entry parameters as well as the departure stage, whether it's reusable or one shot. Okay, now we need to talk about ballistic coefficients. This is the definition of ballistic coefficient right here. It's the mass at entry divided by the blockage area at entry and by the hypersonic drag coefficient during entry. Okay, and hypersonic drag coefficients are usually pretty constant. All right, this is a quantity often referred to as beta. It's measured in kilograms per square meter. Um, Assuming the same proportions and the same gross overall density of the vehicle, then mass scales with the volume, which is dimension cubed. The blockage area scales as dimension squared, which means that all else being equal, beta scales proportional to dimension, to size. Okay, you double the size, you're going to double the beta. Now, where we've been with the probes landing on Mars is up to about a ton and about 100 kilograms per square meter worth of beta. All right. Now, if we look at beta getting larger, but we want to relate this to mass, beta is going to grow as the cube root of the mass to be landed. Now, my view here is obscuring some of these things, but as the beta increases, I ran a trade study with my entry spreadsheet, and as the beta approaches 1,000, we start striking the surface. At 100, we come out of hypersonics Mach 3 at about 25 kilometers. At 4 to 500, we're down to 5 kilometers. At 150, we're just about on the surface, and if we go to 1,000, we're going to be striking the surface while we're still hypersonic. Does that make sense? This is the risk. This is what you got to deal with. All right, now we're going to be talking about what lands has to be stable for the landing. This has already been seen with some of the commercial landers that just tried to touch down on the moon, and they've had troubles because they were too tall. All right, now, nearly all the prior landers, the prior ones in decades past, on the moon and Mars, had a footpad span, that's this dimension here, that was either equal to or greater than the height to the CG. That's this dimension here. Now you can go through some geometry. It's a proven criterion. This actually works. It's Surveyor, it worked for Apollo, it's worked for the Vikings, it worked for all the other probes that landed on Mars and the moon. Okay, you don't want to violate this. That's the proven criterion for rough field landings. If you're going to be tall and thin, you're going to need to land on a paved pad. But we're landing in the dirt. There's no infrastructure on Mars yet. Okay. Now, we want about a half a meter underneath our lander here for the propulsive jet to clear and blast out laterally. All right. Basically, this geometry sets the diameter, that's this dimension, and the L over D ratio, which in turn sets the length of the lander by means of all this geometry right here. And it came out to be just about an L over D of 2 for cylinder shapes. I'm going to presume that this lander is nothing but a cylinder. All right, there we go. Now, I need a lander engine. I wanted to use storable propellants for the landing so that I didn't have to worry about evaporative losses. It's a little lower performance, but who cares as long as it works. All right, so I'm looking at monomethyl hydrazine and nitrogen tetroxide, NTO. All right, now I have a spreadsheet that sizes liquid rocket engines as a function of the technology and all this stuff. And I've got kind of a modest modern technology here. I've got about 2% of the bleed that's dumped overboard. That's coming straight out of the propellants that are drawn from tankage. They're used to run the turbo pumps in the cycle. All right, here at the entrance to the nozzle is where I measure the chamber pressure. It's a modest 2,500 psi. And I'm using a curved 18 and 8 degree bell. My spreadsheet code sizes this out pretty easy. This is a vacuum engine, but I sized it such that at maximum thrust, it can be fired at sea level. All right. it can be fired at sea level without flow separation in the bell. In other words, you can test open air nozzle on the ground, the configuration that's actually going to fly. All right, but it is a vacuum engine. It's over expanded at sea level. It's just not separated. It's right on the verge of separating. All right, so this engine is rescalable. I did it for one thrust requirement, and we can always scale it up and down. Thrust is proportional to the area, and the flow rate is proportional to the area or the thrust. All right, let's see here. I did not push the state of the art. This spreadsheet's available, by the way. Just contact me. I can get it to you. Okay, here's my sizing results, rough sizing results for a stable lander. Okay, I picked a 10-meter diameter. It's kind of arbitrary. It gave me a 20-meter length, gave me at that packing density roughly an 80-ton mass at entry, using an average blunt object CD of about 1.5. Hypersonically give me a beta of about 850 kilograms per square meter. All right. This design concept has a base structure to which the legs and the engines attach below, and the shell and the tankage for the engines attaches above this base structure. Okay. The tankage goes up the core of the cylinder, and the cargo is loaded all around it. We're going to drop the heat shield, which is on the base end of it, at the end of hypersonics, which is clearing the way for the braking engines to fire immediately while you're still traveling at about Mach 3, five-ish kilometers above the surface. The pertinent question here that raises, is there a way not to drop the heat shield and yet still clear the way for the engines to fire in order to avoid a debris hazard? We want to try to mitigate the debris hazard on the ground, because this may not be the first one of these to land at a site. I didn't address that in this study. I just did the basics here. All right. Now, final sizes for the lander. This is what I finally came up with. Here's a sketch of it right here. Here's a view of where the engines are in the base. It's kind of obscured by my image. There's 5 engines down there, and the landing legs fold between 4 of them. And here's the core with the propellant tankage. Here's the cargo that's carried. We'll talk about how that cargo is unloaded in the next slide. We'll worry about that in a minute. Okay, so it's I did this in a spreadsheet. You're welcome to it if you want it, but it's kind of a one-of-a-kind spreadsheet for this lander. I did the rocket equation calculations using that DV requirement that was factored up by about 1.5 or 2. Actually, I did this twice. I did it for the factor 1.5 on the 0.7 kilometers a second, and here's for factor 2 times 0.7 kilometers a second. That's a 1.4. All right. So I sized them out. I actually sized 2 landers. One's a little smaller, one's a little bigger. Okay. That came up with a couple of engine thrust requirements that are not very different. That sort of thing. You can rescale the engines from there. All right. Now here's the entry results. This is based on the old 1953 vintage H. Julian Allen type analysis that was done for warheads back then, was declassified in the late 50s. It uses an exponential scale height density model. It's approximate. It's 2D Cartesian. You have to wrap the results around the curve of the planet. It's crude, but it's surprisingly accurate even today. All right. He did it for only Earth's atmosphere. It was for suborbital warheads that would be less than Earth orbit speed coming back, or under 8 kilometers a second. The heating model in it is only for stagnation convection. There is no plasma radiation. You'd have to add that model if you're going to go much faster than about 9 kilometers a second at entry. It'll work here for this because we're going to enter the Martian atmosphere between 5 and 6 kilometers a second. It should work just fine. For any one planet's atmosphere, there's only 4 pieces of data that you need to input. You've got the speed at entry interface. You've got the angle below horizontal at entry interface. You've got the ballistic coefficient or beta for the entry vehicle. And you've got a figure for the nose radius. That kind of determines how bad the heating's going to be. All right. The entry interface altitude is part of the atmosphere model. Okay. Now my spreadsheet that does this old by hand analysis, I put in a spreadsheet, and I've got atmosphere set up for Earth, for Mars, and for the moon Titan. I got these out of the Justice and Brown entry, descent, and landing paper from a few years back. You're welcome to the spreadsheet. Just contact me. This is good for in the ballpark for screening ideas and getting first estimates, which is what I'm doing here. What you want are the plots, and that's what I put here. My spreadsheet makes these plots. Now this is kind of lets you determine the shape of the entry. I've got range versus altitude, and I've got time versus altitude. Now down here at the end where I'm slowing down, that's where the time goes nonlinear. All right. Now here is velocity versus time plotted all the way to the Mach 3 point, end of hypersonics. And this is the acceleration. You can see the peak G's right before I come out of hypersonics. In this case, the peak G's, somewhere around 2 G's. All right. We're still about a half a G as we come out of the hypersonics there. Now here's the heating. The blue here, this is the heating rate in watts per square centimeter. You can see the peak here at just under 16 for this 10-meter nose radius. All right. It occurs a little earlier than the peak G's. Heating always precedes peak deceleration. All right. Now this is the accumulated heat. If I was conducting heat into the structure or some fraction of this heat into the structure, this number tells me how big my heat sink has to be. All right. Now we're looking at 85 tons at entry, a ballistic coefficient on the order of 850, that sort of thing. It's all the same stuff. Now my spreadsheet pops these out automatically. You're free to adjust the altitudes such that you've got plenty of points where you need them, right where the deceleration is happening here. It's not a big deal. That's the independent variable is altitude. Now, what you can do with that entry model is you can do an entry heating estimate of surface temperatures, which is what I did here. And you can also estimate the pressure on the heat shield that the material has to withstand, which I did not show here. Basically, you can take the mass at entry times the peak G's, and that's the force, the peak force that you're going to experience, and spread it over the blockage area. That's the average pressure on that heat shield, since the ambient atmosphere is so thin that the pressure is very nearly zero. And then double that, and that's pretty close to the peak stagnation point pressure. It's a rough estimate, but it gets you in the ballpark. Your material has to withstand that pressure. Here, the heating, I'm presuming that I've got a refractory heat shield. I could be using an ablative, all right? But I used a refractory, and I estimated some temperatures by balancing the convective heating to the re-radiation, and I needed a black surface to re-radiate efficiently. All right, so I get these temperatures. Now, I do need some kind of ceramic. That 2400 Fahrenheit there is a little high for metal. All right, on the stagnation, that's here on the front. I need some kind of heat shield material to get through entry. I'll be coming in as depicted here, blunt end first. Okay. Now, on the attached flow on the sides, that's roughly factor 3 less heating rate than here at stagnation. That equilibrates out at just under 1900 Fahrenheit. So if I used I could put some kind of heat shielding on this, or I might have bare metal if I care to use one of the more expensive high temperature alloys. Inconel might work, or a stainless steel. I might get away with a stainless 309 or something like that, but Inconel would be better. And then in the separated wake zone here on the back, that heating rate back there is about factor 10 lower than stagnation. Well, that equilibrates at about, well, under 1400. I could easily use stainless 316 or 304 back here. It would work. You could get down. So the heat shield is not that serious a problem for this. Mars entries are just not that bad, even at a little over Mars escape speed. All right. Now we really need to look at the size of the landing pads because 98% of Mars is basically soft, fine, loose sand, dry, or that same kind of sand with loose rocks scattered within it. All right. It's not hard. It's not hard pan. It's not, it's like landing on a sand dune. The earthly allowable bearing pressure for soft, fine, loose, dry sand is a low value. It's, I think it's shown on the chart somewhere. Yeah, here it is, 0.1 megapascal, or just about a ton per square foot in US units. All right. Um, that would be an allowable bearing pressure. It's about half the ultimate or failure pressure, where whatever you're mashing on sinks into the sand. That's a dangerous outcome, by the way. You don't want to stab into the sand. You got to factor up the landing Mars weight of this thing for the dynamics of touchdown and for coming down crooked. I used factor 2 for both of those, so I had to take the weight and multiply by 4. I ended up sizing pads that are about just under 2 square meters, or about 1.5 meters in diameter for 4 pads. They need to be fairly big because you're landing in the soft sand. That's just going to be a requirement. If you stab in on one leg, you're liable to break something or tump over. It's just a risk. That's what you got to plan for. Now, my concept here for the unloading of the cargo is actually fairly simple. Of the side panels on this vehicle, there's 4 of them that simply fold down to become ramps where you can walk right up to the cargo, grab a hold of it, and walk out of here. Now, here's the problem. This is 10 meters, and that's 20 meters up there. That's a ways up there to reach for a man in a spacesuit. You may want to drive some kind of a loader vehicle up here, kind of like a forklift, to be getting this stuff. So these panels, they can't be the lightest things in the universe. They need to be stout enough. The slight curve provides some strength. They're going to need some thickness. I figure there'll be some insulation to protect the cargo from the hot skin. And then over that, we might put a piece of plastic that you could walk on or drive a loader on. Okay. It's going to be a fairly low slope getting up there. We got about 40 tons of cargo to unload. Yeah, okay, that's fine. So we're taking 40 tons of cargo in a vehicle that weighs 80 tons at entry, and we're landing it on Mars. And I've showed you how to do that from a low end of hypersonics altitude and not using any chutes, which since you don't have time to do it. And you can do it in a shape that you can unload. This is actually a fairly practical outcome for the design. All right, now we have a feasible lander. And here's the specs on it. 40 tons in an 80-ton vehicle, one way, one shot off a home and transfer, direct entry. What's next? How do I get it to that point? I need a transfer stage to go from Earth orbit, send this vehicle to that point. The easy one is the one-shot non-reusable transfer stage. The hard one is one that I would have to recover and try to reuse in some way. But I did address both of those. All right, we'll talk about the expendable transfer stage now. Now, I'm assuming departure from Earth orbit using hydrogen-oxygen propulsion. I'm going to burn out most or all the hydrogen and oxygen. And then I'm going to use storables for the two course corrections and probably for the ullage in order to get the hydrogen oxygen to light off. The storables can be pressurized bladder expulsion from the tank. I can't do that with the cryogenic hydrogen and oxygen. I need the ullage solution. All right, here's the requirements for it down here. Here's the it's a little over 3 kilometers a second for the hydrogen oxygen, and a very modest 0.2 something kilometers a second for the storables. That's a fairly easy thing to do. Now we're going to launch from Earth. We're going to do a course correction midway about 4 months later, and then right before we get to Mars, we're going to do another course correction to make sure we're dead center on where we need to be for that grazing entry into the atmosphere at low angle that we have to have in order not to smack the surface immediately. I just budgeted these. They're just budget calculations. They're reasonable. Now, the one-way home and transfer ellipse at average planetary conditions is a 259-day one-way trip from Earth to Mars. That's a little over 8 months. Okay. Okay, I needed some departure engines, so I used my rocket engine spreadsheet again, and I did a hydrogen oxygen engine, again, of modest technology with a little bit of bleed dump, curved bell, modest chamber pressure, hydrogen and oxygen. Okay, and I got some data for the engine, and once again, it's a vacuum engine, but it's sized where I can test at full thrust at sea level and not quite separate the belt, which means I can open air test the full flight configuration on the ground. That's a great savings in development. All right. Let's see here. Rescalable departure engines. I did not push the state of the art. Okay, we got that covered. Okay, now I did another custom spreadsheet for determining the expendable transfer stages, sizing it out and determining the number of engines and all that sort of thing. All right. Now, it's the same, it's it's multiple linked burns. I had to do the departure burn and do some calculations for it. And then I had to do the sum of the correction burns. That's all in one weight statement. So I could just sum those DVs up and do that. And the propellant that's going to be used in these burns has to be carried in these burns. That's the trick that most people forget when they're trying to do this. And I ended up with a vehicle buildup that set the weight statements. Okay, and I sized some engines and I got it all to work at about, somewhere around 1/10 of a G. That should be good enough for impulsive operation where I don't have gravity losses in space. So I ended up sizing the transfer stage with my spreadsheet. Okay. Again, it's custom for this design. There's no general spreadsheet for this. You got to do it yourself. But you're welcome to it if you want it. This is the expendable transfer stage that I came up with. It's got some hydrogen oxygen propellant tanks here. It's got some storable propellant tanks here, and all the engines are riding in this structure here, kind of a truss structure. Okay, it's got a power unit, it's got guidance and control unit that I assume some masses for, and here is the lander payload that it pushes. Nominal 85 tons with 40 tons of cargo aboard. All right, now the expendable transfer stage is this big. Here's the engine layout. The three big circles are the three hydrogen oxygen engines, which only need to function for departure. And then the smaller gray dots are the three storable engines that need to do the course corrections, the two course correction burns. And if you were to put solid ullage motors on it instead of using the storable propellants as your ullage solution, they would be the little red circles here. Now that might be the better solution because it would reduce the size of these tanks and thus the inert weight of the vehicle a little bit. It's a pretty simple design, but then again, it's a one-shot expendable. All right. Now what we have here is my attempt at a reusable stage. I first tried to do this with a oxygen hydrogen departure, and then all the rest of the burns all the way back with storables, and I was unsuccessful. That was beyond the capability of storable propellant performance levels. So I ended up having to do it with hydrogen oxygen the whole way. That means I need I'm going to use course correction burns. I'll do those with the storables here and here at Mars and here on the way back to Earth. But the Earth departure burn is LOX hydrogen. There is a Mars departure burn that has to be LOX hydrogen and an Earth arrival burn that has to be LOX hydrogen. Now there's a complication here. This orbit is not a multiple of Earth's period, 1 year period about the sun. You're going to be waiting 3.39 years. You're going to go around this orbit, this Hohmann transfer orbit, multiple times until you arrive here at perihelion at the same time Earth is there, some 3.39 years later. That's the synodic period. So this stage is going to spend almost 3.5 years in space with cryogenic propellants on board. That's the risk with this kind of design. So it came out to be a little bit bigger stage, and it's going to have some equipment on board to keep those propellants from evaporating away over the time interval of 3.5 years in space. That's a difficult design problem. But assuming that that's possible, you can do this. All right, I did this again with a spreadsheet. You're welcome to it if you want it, but it's custom for only this design. All right, I got some inputs up here, and there's multiple burns. Here's the weight buildup. It supports the weight statements, plural. And then there's multiple burns to be made with multiple kinds of propellants. And the propellants in the later burns is carried as payload in the prior burns. That's what you got to worry about and make sure you get it done right. And then I got to make sure I got to have enough thrust to accelerate the vehicle adequately so that I don't have gravity losses in space. And then I also had to consider engine out and all that sort of thing to make sure I had enough thrust. You're welcome to it if you want it, but that's what it looks like. Okay, this is what the reusable transfer stage looks like on the assumption that we can keep the propellants from evaporating for 3.5 years in space. I've got a cluster of engines back here. I had, I believe it was 9 engines for the LOX hydrogen, and I had some engines for the monomethyl hydrazine stuff. Now here's the LOX tankage, LOX and hydrogen tankage. Here's the oxidizer and fuel for the storables. It's got a power unit. It's got a guidance and control unit. It's got these clusters of engines and ullage solutions back here. Again, the payload is 85 metric tons, 40 tons of which is cargo. And because of the higher performing hydrogen oxygen, I'm only somewhat larger, about half again larger than the expendable. Okay. The main risk is losses, evaporation losses over almost 3.5 years in space. that to be the risk with this design. I did not address that. I don't have a solution for that. All right, conventional wisdom aside, yes, it is feasible to land 40-ton cargo payloads on Mars with no infrastructure to receive them. You're landing in the dirt, all right? You're going to do immediate rocket braking after entry. The expendable transfer stage is an easy thing to design. Reusable is feasible, but I don't know. That one is a tougher design. But basically what I looked at here were all existing technologies that did not push the state of the art very hard. So you're not going to spend yourself into oblivion trying to make advanced technologies work. You're going to be able to put Tinker Toys together and do the mission. That makes the likelihood of success much higher. Where there's no, I assume, no infrastructure on Mars because this is the means for emplacing that infrastructure on Mars. That is what I was doing here. Okay. Now, if you've got any questions or if you want my spreadsheets or whatever, please contact me. The preferred contact is this email. Be aware that the old landline phone here it's an old-fashioned landline phone. There is no text capability. And be aware that because of all the spam calls I get, I typically don't answer the phone if I don't recognize the number. So try to leave a message, and if I'm home, I may try to break in. Otherwise, I'll try to get back to you from the message. Be aware that I have a blog site that has all sorts of content on it, including things about studies like this. And I'm also on LinkedIn. So you've got some multiple ways to try to contact me if you need me. I do thank you, and I hope you enjoyed it.